Hey everybody. I am gonna try to fly through this because I already did one take and it took more than 20 minutes. So I'm gonna try and cut it shorter than that. So this week in our Block 3 POW, we were exploring the 11s trick that Kelsey volunteered in class. So just really quickly, the trick, and we're gonna be focusing on 23 through 28 today to think about this, but obviously it works with other numbers. So the trick, if you remember, was that if we were going to multiply a number like 23 times 11, the way we would do that is we scoot the numbers apart from each other, leave a blank in the middle, add them together, and that's the number that goes in that blank. So in the case of 23 times 11, we get 253. 24 times 11, we get 264. 25 times 11, we get 275. 26 times 11, we get 286. And for 27 times 11, we would get 297. We're going to hold off on 28 times 11 for just a second and come back to it. So what I want you to think about when you think about these problems, I'm going to put our two multiplication parts over here. So we have 23 and 11. So if we think about this as 11 groups of 23, one way we could think about that is 11 decomposed into 10 and 1. And we know the partial products rule tells us that we can do that by doing 10 groups of 23, plus one group of 23. So 11 groups of 23 can be thought of in two chunks. The first chunk is 10 of them, and then there's the 11th group, that one extra that we're adding. So if we think about the problems that way, they become something like this. 23 times 10 plus 1, 24 times 10 plus 1, 25 times 10 plus 1. And we know from the distributive property that we can just multiply those out. But let's try and keep our minds thinking about them in groups. So we have our first 10 groups of 23 is 10 groups of 20, which is 200, and 10 groups of 3, which is 30. Notice that because we have 10 groups, we're not going to have any loose ones. So in this case, our first 10 groups have no additional ones, and that's going to become important in a second. And then we have that one extra group of 23 that we're going to add back at the end. Similarly, when we do our first 10 groups of 24, 10 groups of 20 is 200, 10 groups of 4 is 40. So here, another way to think about that is 24 groups of 10. And since a group of 10 has no loose ones, then 24 groups of 10 has no loose ones. But one group of 24 does have 4 loose ones. And by loose, I mean they're not packaged into a group of 10. So we could go on down the line here and we get 250 plus 25, 260 plus 26, 270 plus 27, 280 plus 28. Let's come back to him at the end. So what I want you to think about is what is the pattern that we see here. No matter what number we multiply by 10 and then one more, because these are groups of 10 or 10 groups of whatever, there are no loose ones in the first group of 10 of them. All of the loose ones come from however many ones were in the original number, because that's how many we get when we add one more group to make our 11th group. So let's think about the pattern that would follow if we add these vertically. So here I've got 23 and 230, right? It's the same problem as over here, but I've just written it vertically. What I want you to notice, let me get rid of the crease here. What I want you to notice So take just a second and notice what's happening in each of these vertical addition problems. What numbers are always being added together? And what numbers kind of do their own thing by themselves? Well, first of all, notice that because the first group of 10 didn't have any loose ones, because it's 10 of them, or in other terms, it's 23 groups of 10, and so since there's no loose ones in 10, no matter how many groups of 10 we have, they're always going to be complete 10s with no loose ones. Well, what that results in is that the first number, the first 10 of them, has nothing in the ones column. But then the second, that last group that we add, the 11th group, has as many ones as the original number did. So the ones place in each of these is always going to come from the ones place of the original column, or the original number, sorry. So that 11th group, so here's the first 10, and here's the 11th. That 11th group is always going to be the source of the ones column, because the first 10 are never going to have anything in the ones place, right? Now let's think about the hundreds place. If our number is a 2-digit number, then the hundreds place is always going to come from 10 groups of 10 groups. So in this case, it's 10 groups of 2 10s, or 10 groups of 20 makes 200, right? 10 groups of 20 and 24 makes 200. 10 groups of 20 and 25 makes 200. So in these cases, the hundreds place, you could think of it as just dropping down, but I don't want to use that language because that kind of looks at just the digit, and I want to think about it in terms of groups. So the hundreds group is coming from how many hundreds are created when we take 10 groups of the tens place. So in this case, we're getting our hundreds place from 10 groups of what the number that was in the tens place here, which is 200. So now we see, because the ones place is coming from the ones place of the original problem, and the hundreds place is coming from how many tens we had in the first place to be multiplied by 10. That's why we can start these by sort of putting, like Kelsey put it, open up a space and copy the original number down. Well, so the only finicky thing that's going on here then is what's happening in the tens place. So I want you to notice, what numbers are we always adding together to get our tens place? Well, let's think about it again in terms of groups. So the first 10 23s makes for 3 10s because it was 3 single numbers, or 3 loose singles, you might think of it, in groups of 10, right? So 3 10s is how many we get from the first chunk of 10. And then we get 2 more 10s when we add the 11th chunk. So the first 10 out of the 11 groups of 23 gives us 3 10s. The last one gives us 2 more. So what's happening is the numbers that get added are effectively the digit from the ones place, because that's become a group of 10 of them, and the number from the tens place, because that's the 11th group. The 11th group has that many tens. So here we have a 6, here we have a 7, here we have an 8, here we have a 9. So it's not magic that makes this happen. It's just that when we add that 11th group, we get that same amount of tens added to 10 groups of the number of ones we had before. So let's think about this weird one. If we add 28 to 280, what we're going to get is we're still going to get 8 in the ones place because there's no other loose ones. But here, we've now created a new group of 10 that gets carried over, right? So when you have something where the first, so thinking of it over here, it kind of becomes a rule breaker. And I have an idea that Kelsey's teacher taught her a what if rule, which was if the two numbers add up to be more than 10, so here you have 8, here you have 2, and in this case, we would actually want to put a 10 in that box. You probably keep the ones place there and move the 1 over. So you would get 308. Similarly, if you were doing 29 times 11, 2 plus 9 adds up to be 11. And so I would imagine that Kelsey's teacher taught her take the tens place and add it to the hundreds, keep the ones place there, and drop down the 9. So again, the reason is because if we had, for instance, 290 plus 29, the number of tens that we got by doing 10 groups of 9 and the number of tens we got by adding one more group of 29 rolls over into a new 100. So the reason this works with 11 is it's not some magic trick. The reason this works with 11 is because you're adding exactly one more of them. So I want to think about one other way to think about this, and that is by going to our old friend, the distributive property. So think back to yourself about how you would do this problem. Do you remember doing these problems in algebra? You probably do. So we multiply the firsts, then the outsides, then the insides, then the lasts, right? So FOIL. So think about this. When we were doing, this representation shows decomposing the 11. What if we decomposed the other number? So what if we were doing 25 times 11 and decomposed both numbers into 20 plus 5 and 11 and 10 plus 1? Well, that would give us something like this. 20 plus 5, 10 plus 1. So here's what I want you to notice. Where is the ones place going to come from? Well, so if we do our FOIL, so we get 200 here, plus 20, plus 50, plus 5. In every case, so let's do 34 times 11. So 30 plus 4, 10 plus 1. In every case, what multiplication problem is always going to create the leftover loose ones? Well, it's always going to be the ones place from the first guy times the one place from the second guy, which in this case is 4 times 1. So what's unique about 11 is that the ones place in the second number is a 1, which means that you can predict what the ones place will be in any of these numbers. So if we did 42 times 11, I can know that foiling it out is going to give me a 2 at the end. Sorry. If I do 37 times 11, I know that the ones times the ones is always going to give me a plus 7 at the end. Well, what about the hundreds place? Well, the hundreds place, as long as we're doing times 11, where there's only one group of 10 in the second group, the hundreds place is always going to come from the multiplication of the tens place in the first column and the tens place in the second, which in this case is 300. In this case, it's 400. In this case, it's 300. So all that's really kind of up for grabs is the stuff in the middle. So that's another way to think about this problem, and I encourage you to explore that and ask yourself, could we figure out the pattern that's happening if we do 3-digit numbers? I would bet Kelsey's teacher taught her a rule for this, but I think you can figure out what it is if you do a sequence of them like this. In other words, do your own private choral count with 11s, beginning at a number like 234, and see if you can see what the pattern is and why it works, and how to translate that pattern into a quote-unquote rule. If you have further questions about this, I'm happy to explore it with you. I would encourage you to try and figure it out using the pattern, and try and figure it out using arrays, because I think that'll help you think about it as 10 groups of 234 plus one more group of 234, and how those digits are always going to work in pretty predictable ways. I will see you tomorrow in class.